All right, let's talk about the pH scale. pH just stands for the power of hydrogen, and it's going to just be a nice, convenient way for us to be able to represent the solution acidity. pH, we're going to define it as equaling the negative log of the hydrogen ion concentration. Reason we do this, anytime you log something, it's usually because the number you're looking at is really small, and hydrogen ion concentrations tend to be really small, especially if you're working with a smaller concentration solution. So if you'd have something that's like 1 times 10 to the negative fourth, that's a tiny number. We don't like writing out that number. So for convenience sake, we refer to the power of hydrogen, or pH. If you take the negative log of 1 times 10 to the negative fourth, you get a much nicer number to work with in 4. So yeah, it's just a compact way to represent solution acidity. As hydrogen ion increases, the pH decreases. So if you're thinking about strength of an acid, the lower the pH means the stronger the acid. 7 is neutral pH, so that's the middle ground. If we want to think about why that is, if we can remember Kw equals H plus and OH minus. And if we remember what these numbers are for a neutral solution, for hydrogen, that's 1 times 10 to the negative 7. And the reason that these numbers, 1 times 10 to the negative 7th, is because they have to both add up to 1 times 10 to the negative 14th at 25 degrees Celsius, right? So for a solution to be neutral, the hydrogen ion must be 1 times 10 to the negative 7th, because that's the only number that will allow the hydroxide ion concentration to be equal. So there is where the 7 comes from for neutral pH. If you're greater than 7, then you're basic. The higher the pH, the more basic, obviously. Can we get higher than 14? Yes, we can, with incredibly strong bases. And then less than 7, you're acidic, and of course, the lower the pH, the more acidic. Can we get less than 0? Yeah, we actually can. So the pH scale, just to give you an idea of where some common things lie on the pH scale, blood is a little bit more basic than neutral. Very small range in which our blood can actually fit in. If it gets higher than that, or if it gets lower than that range, really bad things happen. And the body has a pretty cool buffering system that we'll talk about later on in this unit that keeps us within that range. Pure water, obviously 7. Milk is a bit acidic, and then you lower yourself to the bottom, you get vinegar and lemon juice and stomach acid, and then 1 molar HCl is down by the 0. And then if you climb up the pH scale, ammonia, which is usually present in most household cleaners, if you look like a glass cleaner has ammonia in it, about 12. 1 molar sodium hydroxide is about 14. So again, we can scale above those values, but those are just kind of the common values, that 14 to 0 range. Okay, so let's do some work with this. We're going to calculate the pH for each of the following solutions, just to get an idea of how the math works. And again, logs aren't always the easiest things to work with, so we want a bit of practice. The first one's pretty simple. We are just going to take, so we're going to look for the pH, which is just going to be the negative log for the first one of 1 times 10 to the negative fourth. And when we do that, we're going to come up with a value of 4.00. Let me erase that one. Okay, now one thing I want to stop and talk about here for a second are significant figures, because with logs, they're a bit weird, and I know we'll run into this at some point on test quizzes or the AP test. Here's the rule. You go look at the number that you're given. So in this case, it's the concentration of the hydrogen atom. And you ask yourself, okay, how many significant figures are in that number? Well, this number right here has a total of 2 sig figs. So for the rule of logs, as far as significant figures are concerned, the number of sig figs that you have in your original number, in this case 2, equals the number of digits to the right of the decimal place. So you can see that it's 4.00. Okay, 4.00. All right, let's look at a little different case now. We have the concentration of hydroxide ions in part B, and that's 0.040 molar. What we have to recall is that Kw equals the concentration of hydrogen ion times the concentration of hydroxide ion. Because right now, all we know is pH equals negative log of H plus. So we need this number. Well, we found out in the previous video that if we multiply these two together, H plus and OH minus, we get 1 times 10 to the negative 14th. So if we go ahead and substitute in 0.040, and for this guy, we have our unknown, it equals that. We should be able to rearrange and find that our H plus concentration is 2.5 times 10 to the negative 13th. Okay, 2.5 times 10 to the negative 13th. Now, we can take the negative log of this number, and that's going to equal our pH. Because this number right there is that hydrogen ion concentration. Okay? And if we do that, we're going to come up with a number 12.60. There it is, 12.60. Okay? And if we do have a concentration of hydroxide ions that's pretty darn high, like it is here, 0.040, we should have a pH that's certainly above 7. Let's try another one. We get a pH of a solution is 5.85. We want to kind of go in the reverse now. We want to know what the hydrogen ion concentration is. Again, our equation is this. pH equals negative log of H plus. Okay, but now we're kind of working our way backwards. So to do that, we just use the power rule. H plus equals 10 to the negative 5.85. Again, this is just rules of logs, right? Okay, to the negative 5.85. And that's how we kind of get rid of that log. And we'll come up with 1.4 times 10 to the negative 6 molar. 1.4 times 10 to the negative 6 molar. Again, two numbers to the right of the decimal. So that's what we have to have here. All right. Now, pH isn't the only acidity scale that there is out there. We have another one too. It's called pOH. So just as pH stands for power of hydrogen, pOH stands for power of hydroxide. And when we're working with basic solutions, sometimes the power of hydroxide is more convenient to work with. So again, let's recall that Kw, the acid dissociation constant for water, equals H plus times OH minus. If we negative log everything, we get the negative log of Kw equals negative log of H plus minus log of OH minus. And what we find is then that is now our new P. That's our power Kw equals pH plus pOH. Okay, if we remember, pH equals the negative log of H plus. So you can see we're just kind of substituting this in right there to get pH. We'll do the same thing with that guy to get pOH. Okay, so we've come up with essentially a new equation, this guy right here, and I believe the AP chemistry cheat sheet has that equation on it. pKw equals pH plus pOH. And we know that pKw, or we know that Kw is 1 times 10 to the negative 14th, so pKw has to be 14. pKw has to be 14. So 14.00 equals pH plus pOH. So if you know the pH of something, you can very easily find its pOH just by taking 14 minus that pH, and you figure out the pOH. Okay, again, let's do another problem. Let's calculate the pOH for each of the following. And we get a 1.0 times 10 to the negative 4th molar hydrogen ion concentration. Well, we know that pH equals the negative log of 1.0 times 10 to the negative 4th. Okay, if I do that, that should equal 4.00. And I know that 14.00 equals my pH plus my POH. So POH equals 10. Okay. And then we could kind of find the same manner for the bottom. We could figure out the POH by just working POH equals negative log of OH. And that one's a little bit easier, and it'll give us a value of 1.40 if we have that large molarity of hydroxide. Now notice something, this is kind of confusing. Look at the POH. POH and pH are flipped. So a low value of POH means a high hydroxide ion concentration. So if you want a basic solution and you're looking at it in the mind of a POH, it is going to be a small number, not a big number. Okay, let's do one more. The pH of a solution is 5.85. What is the hydroxide ion concentration for this particular solution? So again, if we're given pH, we probably have to get that back into POH. And we're looking, at the end of the day, for that guy. So I think what I'm going to first think of in my head is, well, I know KW equals the H plus concentration times OH minus. Okay, so if I want OH, I'm going to need this guy, and I know that guy. All right, so pH equals the negative log of, let's see, let me rewind that back, because I know my pH. There we go. So 5.85 equals the negative log of H plus. Again, 10 to the negative 5.85. Okay, that's going to equal what we had seen the last time. Forget what that was. Do it on my calculator quick. So that's 1 times 10 to the negative 6. Times 10 to the negative 6, that's my hydrogen ion concentration. So my hydroxide ion concentration, I might go ahead and erase this. I might back this one up, guys. Let me do it one different way. Calculator too much. Let's just remember this. pH equals our negative log of hydrogen. And our POH equals our negative log of hydroxide. Yeah, this is going to be a little bit easier. And 14 equals pH plus POH. There we go. All right, so we know that 14 equals 5.85 plus POH. So POH is going to equal 8.15, right? There we go. Now, if we take 10 to the negative 8.15, that'll give us our hydroxide ion concentration. It's probably going to be a little. It's 7.1 times 10 to the negative 9. There we go. Okay. So it's a matter of just kind of understanding your equations. Say this guy, you got to have that guy, and that guy. And it's nice that the cheat sheet does give us those equations. All right. Okay. 2 more slides then. In 14.4, it talks about something called the major species. It's going to be really important as we carry on with these acid-base problems, especially when we get into weak acids and weak bases, that we think about what are the major components inside of our solution. Because it's only the major components that will give rise to pH and POH. So these things are hugely important in acid-base chemistry. The major species are kind of defined as the solution components present in relatively large amounts. So let's just take a look at a 1 molar hydrochloric acid sample. You've really got 3 things inside of there. You've got a bunch of water, you've got chloride ions, and you've got hydrogen ions. Now, do you have hydroxide ions? Sure, but it's an incredibly small amount of them, so they are not a major species. Okay, so those are the 3 things that we have present. So why is this important? Well, let's take a look at this example where we have a pretty small concentration of hydrogen ions. I'm going to ask you to calculate the pH of a 1.5 times 10 to the negative 11th molar solution of HCl. Here's what you might do at first glance. You might say, well, that's pretty simple. I know pH equals negative log of 1.5 times 10 to the negative 11th. And then you'd come out the back side and you'd say, oh, well, it's 10.82. That's our pH. Okay? And I would say, no, that is not right. Because this answer neglects the fact that water actually dissociates. Okay, remember, in a neutral solution, water has a hydrogen ion concentration equal to 1 times 10 to the negative 7. So water in this case gives 10,000 more hydrogen ions than does this HCl. So water is actually the major species. So it is the thing that affects our pH. So when we're trying to find pH, we do not use this number, we use this number. And if I take the negative log of this number right here, my pH is going to equal 7. So that's why it's important to understand the major species. We want to know what's in abundance. The hydrogen ions from the HCl are in such low concentration that they don't affect our pH. Okay, that's 14.4.